Hello everyone and welcome to today's session of virtual lab on signal processing. I would like to welcome, I would like to extend a special welcome to our presenter, Dr. Brijesh Kumar Kaushik. And for those of you just joining us, welcome. The main objective of today's session is to provide remote access to virtual lab on signal processing. These labs would cater to students at the undergraduate level, postgraduate level, as well as to research scholars. Now I am handing over this session to our speaker, Dr. Brijesh Kumar Kaushik. Over to you, sir.
Yeah, thank you very much, Mr. Ashish Bhatt, again for inviting me for today's session. So actually today we had planned to do something on digital signal processing. So I'll be taking forward all this talk and I'll be giving a brief overview actually about this V labs, virtual labs, before we start up other things. So I'll just start sharing my screen and we'll take you to the V labs portal. So hope so all of you are able to visualize it. This is vlab.co.in.
Yes.
So in the interest of all those who are joining us for the first time, for them actually I'll be giving you a brief overview actually about how this website works and what kind of experiments are available and what kind of different areas we can cater to. So you can see this is a portal which has been developed by an initiative from Ministry of Human Resources Development under the National Mission on Education through ICT. So objectives are very clear to give you a virtual lab access to the students at undergraduate, postgraduate, as well as to the research scholars. So yesterday I just came across one of the queries that whether we can use this platform for our research purpose and can we quote the results that we obtain through this website in our research papers? Yes, of course, you can do that. And this is something to support students at all level, let it be at UG, PG or at research level. And of course, as I told yesterday also, I would reiterate the same thing. This is the right time when we can use all these virtual labs for especially the students and the community who are suffering due to this COVID. So probably we all cannot access labs directly. And in this time, RGPV has really initiated a nice initiative where we can look into the virtual labs that can be accessed. So you can see on the portal itself, there are broad areas of virtual labs and it caters to many labs actually and to many engineering streams also. So if you see on the top, you have your electronics and communication, then you can go for computer science and engineering, electrical engineering, then your mechanical, chemical, biotechnology and biomedical engineering, civil engineering, physical sciences, and chemical sciences. So there are a lot of actually branches to which it can cater to. And each of these branches will have number of subjects, areas, and within this subject area, there are plenty of experiments that can be taken care of. So this is something which is really a good measure from MHRD for all the candidates. So the participating institutes which you are seeing, which is scrolling on the bottom of your screen, is the institutes who have actually contributed to this initiative. So you can see IIT Madras, Dayalbagh Educational Institute, NIT Kurukshetra, College of Engineering Pune, then you have IIT Kharagpur, IIT Roorkee, where we are sitting and we are contributing to this V Labs. Then also IIT Guwahati, IIT Delhi. So all these institutes have actually contributed by one way or other way to each of these subject areas and to each of these lab sessions. So as informed by RGPV community that in fact they are more interested in electronics and communication. So this is how you can go to electronics and communication by clicking it. And then you can see the labs which are ready, which you can use for your students as well as for you as well. So the labs ready for use means the labs which have been tested properly, which can be used by the candidates. So fading channels and mobile communication lab is there. Then you can have advanced network technologies virtual lab. You have analog signals network and measurement lab. Then you have your digital electronics lab, digital logic design lab, queuing networks modeling lab, hybrid electronics lab, RF and microwave characterization lab, which is really not easily available RF and microwave characterization lab. Then you have your digital electronic circuit lab, DSP lab, which will be looking into digital signal processing today. Then yesterday we had gone through basic electronics lab. Also there is signals and systems lab, electric circuit lab. So there are a lot of labs which can be actually looked into. And there are few labs which are under development also. So there was a lot of demand for digital VLSI design virtual lab, which is now under development from IIT Guwahati and would be available. So some of those experiments still you can look into, which can be taken care of. I've just clicked some of them. So you can see that the lab would be catering to the needs of MOSFET, CMOS inverter, ring oscillators, logic gates, multiplexer, then your latches and registers. So all these labs would be available. And also you have satellite modeling and simulation lab, electronic instrumentation lab, then your EDC, that is electronic devices and circuits lab. So all these labs are under development, and hope so that most of the people across India would be using it, not only in India, but out of India also this is being accessed. And you can see that the related NPTEL video lectures are also available to cater to the needs of the students. So I believe the students who are really willing to go ahead with the lab sessions, I think this is one platform where they can explore many things while sitting at their home, doing many things regularly. So this is one good opportunity, I believe. So as told, we'll be going through this digital signal processing lab. I just clicked the DSP link, and you can see that when you click this virtual labs, digital signal processing virtual laboratory, you'll have an introduction of the lab, which is there in the front of your screen. Then the list of experiments over here, then different frequently asked questions, then the people who have been responsible for development of this lab, the feedback mechanism in case you feel that no, this is not a good solution, probably you can have something more than this. So you can send your feedbacks also through this medium. Then the technology which has been used to develop all these kind of lab, that is also possible to see over here. And of course, you can add a few things. You can suggest few things to the developing institute to actually add few experiments as well. So I just click on the list of experiments. This is quite elaborate experimental list, which is available for DSP virtual lab. If you see, people start from sampling theorem, effect of undersampling, and so on and so forth. That we'll be covering today. Then you can see that you have the study of quantization of continuous amplitude, discrete time analog signals, that will be taken care of today as well. Then you have compounding techniques. Based on that, you can read out and you can do certain experiments. Also today we'll be doing this LTI, linear time invariant system. We'll be studying this thing. And you can look into different other mechanisms also, different experiment list also, such as convolutions, your DFT, discrete Fourier transforms, then different transform domain properties. Then also, which is very popular among the students, is your FIR filters, right? So low pass, high pass filters, then your band pass and band stop filter for these FIR, finite impulse response. And also you can look into different IIR filters also, infinite impulse response. So this is something which is really good for the students at all levels. They can explore all these kind of stuff while sitting at home. So the first experiment, if you see, is related to study of sampling theorem, effect of undersampling, so on and so forth. So each of these lab sessions would be supported by different theory also. So the theory would be explained here, and the introduction actually lets you know what kind of experiment is going to be done and what the student is going to learn out of it. So if you see, this experiment enables the student to learn how to view the real life analog signal with an oscilloscope. So while sitting at home without making too much of efforts, you can see how this analog signal can be seen on an oscilloscope, then how to set the amplitude, frequency and phase of a signal source, then how to set the sampling frequency of the source such that the signal is exactly reconstructed from its samples. So I believe there are few basic things which student has to learn, such as your Nyquist criteria and other things that they can learn also through the theory. And if you see, the principal objective of this experiment is to understand the principle of sampling of continuous time analog signals. So you can see the supporting theory is also there. I believe the students or the faculty members who are online, they can, in parallel, they can look into their virtual labs also. They can open up some of the portals and they can look into how this is going to work out. They can have a hands-on feeling about all these things. And then you can see in this theory, there is a complete description about ADCs, right? So the block diagram is there, and then how the sampling is going to be done, at what rate. So how the rate is going to actually affect the sampling. So the discretization of analog signal has been shown here. Then the frequency of sampling, what should be that frequency of sampling? This probably most of you might be knowing that the frequency of sampling must be at least twice of the maximum frequency component of the original analog signal. So this is Nyquist criteria, which is quite famous across the communication and DSP people, right? So this sampling theorem is will be looked into. We'll be going into all this Nyquist rate and all those things, and the Shannon's sampling theorem. All these things we'll be looking into, right? So we'll be reconstructing the signals, looking into all these aspects, and then this is one acute tab where you can see the procedure also. So how to use the experimental setup, right? So there is a simulation engine which is running in the background, and that simulator, either some of those simulator has been developed at these institutes, the developing institutes, or we have been using some standard simulators also, right? So no worry about whether those things have been paid or not, or they are licensed or unlicensed. So when you work on virtual lab platform, it's all licensed for you. You can use it properly. So you can see the procedure has been very elaborate here. You can click into the experimental tab. You can look into all these aspects, go step by step, and find out how the amplitude or frequency or phase angles have to be put into, and how you can change the sine wave generator. And also you can look into the sampling frequency, how you are going to change it out, right? And then you can make different measurements, right? And also you can make different connections. You need to see whether the connections are proper or not. So these are the steps, and then you can see all these signals on some, maybe on some platform, right, which is very similar to your oscilloscope. You can look onto all these aspects. You can see where and what frequency is there, and how you can measure all these things. So all these steps are there, and I'm being supported by one of my research staffs, who will be taking you through each of these steps, right, and letting you know. He'll be spending time onto it to make you understand how the simulator is going to work, how the different conditions have to be taken into, right? So these things we'll be looking into, and his name is Gyanendra. To just save the bandwidth, I'll be just switching off my video. So over to him.
So after the brief introduction to the initiative by the initiative for the virtual lab, now we will proceed to the DSP lab. So we will perform our experiments one by one. Let us start with the first one. So this experiment is all about a study of sampling theorem and effect of undersampling. As we know, the signals are broadly classified as analog and digital signals. Analog signals are characterized by continuous amplitude and continuous time variations, whereas digital signals are characterized by discrete amplitude and discrete time variations. all the signals that we come across in real life are either analog or digital. Analog signals, and the signal processing is done on digital platform. Thus, the analog signals are converted to the digital signals. For this purpose, we do sampling and quantization. So let us perform the experiment to verify the sampling and effect of undersampling. So we see here the array of pixels that remind us of breadboard. So we proceed through this browse block buttons. First click on browse blocks. And a window pops up here that contains 3 blocks. First one is sign generator. Second one is sampling block. Third one is virtual scope. The sign generator generates sinusoidal signals. The sampling blocks takes the sample out of the sinusoidal signals, and the sinusoidal signals and the samples both are observed with the help of this virtual scope. So as per our requirement, we drag these 3 blocks and interconnect these 3 ones. So in order to select any of them, we just click and click on them. It is selected now. Now we drag the white space here. Here, as we click here, where Windows pops out here again, it has 3 parameters: amplitude, frequency, and phase. So here we can set the amplitude, frequency, and phase combinedly. For simplicity, we just take the amplitude 10.5 here, and the frequency we set to 2 kilohertz. Phase angle, initially we are taking 0. Now we click on OK button, then this window disappears. Again, we select now the sampling block. This sampling block takes the sample from the sinusoidal signals and passes the samples to the virtual scope. Again, we click on this block. This is selected now. We drag and place in this white space. So after placing it, we find again the Windows pops up here. Here we can set sampling frequency. So sampling frequency, let me set here 5 for simplicity. Now once we set the sampling frequency, we find the number of samples automatically is decided, it is 10. Again, we click on the OK button, this window disappears. Next, we have to select this virtual scope. So again, we click on this virtual scope, it is selected now. We drag and place here. So one thing that we prefer here is all 3 blocks are in the same line. That helps in getting a good wiring connection. The next, we have to connect all 3 blocks. So we find here all 3 blocks have some arrow type structure. Here, here, here. Virtual scope has 2 structure. So these arrow type structures are used for transmitting the signal and receiving the signal. So we have to connect all 3 blocks as per our experiment. The virtual scope will take 2 inputs. First input it takes from signal generator, and the second input it takes from the sampling block. So now we have to connect all these 3 blocks. So to connect the 3, at first we will connect the sign generator and the sampling block. We just place the cursor here, and we find there is a reddish type, area becomes red. Now we proceed further. We find a pen-like structure appears in place of cursor. So we select here and move along the line. It becomes red and bluish type area becomes bluish type. We move And as we approach the next block, it becomes red. Once it becomes red, we have to drop our signal here. Now what we find, the sign generator and the sampling block both are connected now. Next we have to connect sampling block and the virtual scope. Again, we will place our cursor here. It becomes red. So we select here by clicking at this point and move along the line. And as the area becomes red, that means now we have to connect it. We connect this. Now the sampling block and the virtual scope both are connected now. The next signal, the virtual scope, will take from the sign generator. So we find here we have only one input, one output port here, sign generator, but the output port of sign generator and the input port of sampling block, the wire that is connecting these two blocks can act as port now. So we just place the cursor here. Along this wire, we find a pin type structure appears here along this line. So we can take output from anywhere. This output is output of the sign generator. So we are clicking here and we just go up in this manner. Again click here. This line becomes red. Red, why this is red? Because it has one end and the second end is floating end. So that's why this becomes red. Now we proceed further. Again we click here. Again we are getting the connection in red color connection. So red color connection indicates that the one end is floating till now. Next we move to the virtual scope. As we move the port of the virtual scope, it becomes reddish type area. Then we click again. Now what we find, now all the three blocks are getting connected. The sign generator is sending the signal to sampling block and simultaneously to the virtual scope. Sampling block is taking the signal from sign generator and sending the signal to the virtual scope. So virtual scope has two input now. One is from sampling block, the second one is from the sign generator. So next we click on the virtual scope here. What we find, a window opens and we find this one is the continuous signal, is the sign signal. This is the sign signal and the green one is the samples. So we can set amplitude, sampling frequency of the sample and the phase angle, all these constants from this window also. So for simplicity, we have changed all these things. Now we change the phase angle. We change the phase angle by 15. See what happens. The signal moves towards the left. Next, we change to 30. Again, signal moves towards the left. We change the signals by phase angle by 90. Signals toward the left. So in all these three cases, what we find, our sampling instant starts with the first sample, origin. This is the first sample, green here. The next sample is here. The next sample is here. Again, the next sample is here. So for a complete structure, we have 1, 2, and 3 samples here. Now, sampling frequency we are increasing 25. What we see, the number of samples has increased now. Similarly, we can change the amplitude here also. This is any way we can change the amplitude. You can either scale up or scale down. This is the frequency of input signal is 2 Hz. Now we set again the phase angle to 0. So what we observe finally here, once we increase the sampling, we have lot of samples. So what is the purpose of sampling? Because we have to change the analog signal into the digital signal. So for this purpose, we are taking the samples here. So in this sampling, in this process, we are taking samples out of a continuous signal. So these samples intend to reconstruct the original signal. So original signal is have frequency of 2 Hz only. So here two cases arise: oversampling, undersampling. So what is the Nyquist criteria? We all are known with the Nyquist criteria. So Nyquist criteria suggests that if we sample any signal more than twice of the maximum of the sample frequency of the sample signal, we can reconstruct the signal with help of the sampling samples. So here we are now following the Nyquist criteria. I set the frequency to 4 Hz. What we find here, for a given clock pulse, for a given period of sinusoidal signal, for one period, we have 2 samples. So now we are changing the phase. Now see here, for a given period, from this point to this point, we have taken only 2 signals. So with the help of these 2 signals, we are in a position to reconstruct the signal. Now we'll study the case of undersampling also. So for this purpose, it will be better if we increase the frequency to 6 kilohertz. And for convenience, we are setting the phase angle to 0 degree. Okay. Now the frequency set to 3 Hz here. So what we find here, for a given period of the time, we are taking only 1 sample. Again, for the next period of the time, we are taking only 1 sample. Again, for next period of time, we are taking the 1 sample. That means with help of only 1 samples, we are not going to reconstruct the whole signal. This is the undersampling. So now again, for the simplicity, we are increasing the phase angle here, 45. Again, we see for the given whole period, whole variation, the selected sample cannot present the whole variation here. So the mathematical expression is here: yn equal to a sine twice pi f pi fs. Fs is sampling frequency. This is the frequency of the given signal. N is the sampling instant, and phi is the phase angle. Now we have one more button here below. So before understanding, now we will set it for Nyquist criteria at least. This is 5. This is 10. So here we find there is a cursor. By moving the cursor, we are selecting something, and we see in the window below n equal to 1. That time the value of yn is minus 3.53. Again, we move forward at a time. It is in millisecond. The red one is selected now. For this red one, n equal to 2 and yn is 3.53 now. So by sliding these 3 and more values and all the values we can get by sliding the cursor here. So this is now this after closing, we want to close, we will click here the cross sign and the window disappears. So this is all about the study of sampling theorem and effect of undersampling. Now, right? Now we will see one more thing here about the cross connections and some discrepancies in the connections. So we have 3 more buttons: take a snap tool, undo, reset, and one more is here, help. So with the help button, we can understand the whole procedure also. And with the help of reset, just once we click the reset button, what happens? See, all the connections disappears now. Okay. Now again, we are connecting this sign generator. Okay, sampling block. Okay, okay, and with help of undo, what we are doing, we can just go one step back. Clicking on undo, we get one step back. So again, we are constructing here for simplicity. Now I want to make you understand about the connection, because it is critical here. Sometimes it becomes very difficult to understand how to connect this properly. When it is red, it is fine. It is red here, we start from here. If we drop the signal here or even here, it is red. That is, the connection is not proper and it will not work. So we can do undo here. But one thing mentioned here, again, because we have not ended the line, that means the connection is a floating type of connection. So this one still remains like a pen type structure. The cursor remains like this pen type of a structure. It remains like. So we press the undo button here, it disappears. Still it remains like this. Then go for reset. Still we find it remains like this. We find a pen-like structure here. So to avoid this kind of things, we have to restart this. We'll click browse button again here. So if we do some wrong connection, it becomes very difficult to make it in working condition. So before proceeding this experiment, one should be careful about this connection also, because connecting the two blocks is some tough here. One more thing here, I want to make you understand. Okay, with help of undo, we can replace back, placing here. Okay, so here also we select here and directly connect here. We can connect like this way also, but it is also not preferable. Sometimes we are facing issues in this type of connection. So undo here for this kind of connections. And how we can do the better way connection in better way, we select some here line. So this is the better way that we should prefer, and avoid this cross type of connections and connecting in midway like this. We do undo here. Here we can see we start the connection here, and we just drop at any point, it becomes red and still remains red until unless it is not joined to the either input of a block or output of a block. So here we will go like this. Again, we follow the path and end here. This connection is preferred. So I hope this is now clear to you. And next we will proceed to the next lab. Next experiment. So the next experiment that we study is a study of quantization of continuous amplitude discrete time analog signals. So directly we proceed to simulator. We'll perform our experiment here. So the quantization, the purpose of quantization is to quantize the samples that we get after the sampling, and a value is assigned corresponding to the range of values. Okay, again we will proceed in the same fashion. We have to go through the browse block buttons. We click here the browse block buttons. Now we have a window pops out here that consists of 4 blocks. The first is the signal generator. The signal generator The second one is the sampling block. The third one is quantization block. And again, we have a virtual scope. We all are known with the signal generator, sampling block, and the virtual scope. Now, the new in this experiment is the quantization block. So how these quantization blocks and this quantization works, let us see. Again, we will select the sign generator here. By clicking this, we select the sign generator, we drag it and place here. Here we have now two options. The first is sinusoidal signals. The second one is user-defined signal. Here we can define the signals as per our need. At first, we consider the sinusoidal signal here. Here again, we can set amplitude, frequency, and phase angle. So amplitude, let us set is a 5. Frequency set as 3. And phase angle, just keep 0 degree for convenience. We can keep anyone between 0 to 360 degree, because you know the sinusoidal signals have a period of 360 degree. After 360 degree, it becomes same. It provides the same value. The phase angle is 0 here. Again, we click on the OK button. We find the window disappears. Next, we go for sampling block. We select the sampling block, drag it in this space and put here and click on this block. Now again we find a window here. Here we can set the sampling frequency. Earlier what we have taken the sample of the signal 3. Let us set it as 45. It is oversampling, case of oversampling, because we are Nyquist criteria suggests for 6 kilohertz and we are taking 45 kilohertz. This is the case of oversampling. And we find the number of samples here is 90. And again, we press the OK button and window disappears. Next, the quantization block. We select the quantization block and place here quantization block. So number of quantization bits, here we select 5. And it is, we have 3 options. Only one option is active here, linear quantization. And press the button OK. Next, we have a virtual scope. Again, we select the virtual scope by clicking it and we drag it here. So this is the virtual scope. So the virtual scope has 3 input now. The first input, it takes from the sampling. At first, we have signal generator that generates the signal, and the signal generated is the amplitude 5 volt, frequency is 3 kilohertz, the phase angle is 0. Now we go for sampling. The sampling frequency is 45 kilohertz. It creates 90 samples. Again, we go for quantization. This quantization is of 6 bits. Here you can understand this theoretical part here. Theory block, theory window is also here. The highlighted window is the theory window. By clicking this, we can go through the theory also. The references are also here for better understanding. You can go through this one also. So linear quantization, okay. Now we have to connect. Again, we have to be very careful about this connection, connecting the two blocks. So with the sinusoidal signal generator, again we have an arrow type of structure. From here we take the output and we just click here and proceed next. Here. Again, what we find, the circle that we saw, it becomes some reddish and brownish type. Now we click here. So these two blocks are now connected. So the sampling block is now getting the signal from signal generator. Now the sampling block, output of the sampling block is sent to virtual scope directly. Now we have to send this signal to virtual scope. So how we will send this signal to virtual scope? We just select here. Again, we drag and the pen type, cursor becomes pen type. And we click here and proceed on these lines. We find in between the circle is some bluish type. As it approaches the port, it becomes reddish type. So when it approaches the port, it becomes red, just click here. Now the sampling block and virtual scopes both are connected. Similarly, the virtual scope will take one output from the signal generator. So signal generator, as we know, the interconnecting lines are act as the port. Here we can take the sinusoidal signal. So once we approach the interconnect line, we find the cursor becomes the pin type. Again, by clicking it, we select it and we proceed further. Click here. Again, this the red line. What is the red line? Red line indicates the floating connection. Floating connection means one end is connected, another end is not connected. We proceed in this fashion here. Again, click here. Now this point and this point is connected now, but still the connection is floating in. Now we proceed, come below. What we find? It becomes reddish. The area around the red point becomes reddish. That means now we have approached the other end. Now we click here. The connection is done here. Similarly, the virtual scope gets output from the quantization block. And for the quantization, we quantize the samples that we are obtaining from the signal generator. We don't have any port here we find. So the interconnecting lines between the virtual scope and the sampling block acts as a port like a structure. That means that from here also we can get the samples. Now we take the samples from here, we move. We click here, line is red, simply it means it is floating in. We approach to the quantization block. Again, what we find, it becomes a reddish type now. So we place here. So the sampling block and quantization block now both are connected now. Similarly, we have to connect now quantization block and the virtual scope. The output obtains from here. Once the cursor approaches the arrow type structure, it becomes red. Now we take the signal from here and we click here. The wire is the floating in, as discussed earlier. Now again we proceed up. Okay, what we find? Now this is connected. So this is the setup that will be used, that is used for the quantization of continuous amplitude signals. Now we will click on the virtual scope. What we find? See here. This is the output. So here we can vary our sampling frequency, amplitude, frequency of the input signal, phase, all things can be changed here. Similarly, we have one more cursor here. By selecting, we are selecting the corresponding signals for corresponding time. By sliding this, we are just changing time, and the rest other things are changed automatically. We are getting the data corresponding to this in this fashion. So let us do some more experiment. We change the sampling frequency to 30. See here. Or just now we keep 45. See here. So amplitude here we can change also 5, 10. See here. 5. By simplicity, for simplicity, we keep the amplitude 5. Now this is the frequency of the input signal. That can also be changed. See, this is now. So what we find, sampling instant remains same considering the sampling signals. So the sampling is instant. Here we set the frequency just 3. So sampling is instant, still remains same. So for changing the sampling instant, we change the phase angle. Now change the phase angle to 45 degree. Now see, the sampling instant moves. So this is all about the experiment here. And one more option we have, just clicking here, we can close.
In the sign generator, we have one more option here. This is user defined signal. So user defined signal, we can type the equation below here. So what we can type as per our need. We can what kind of signals that we want to adjust here, we can type here. So the question mark shows we can take suggestions from here also. We start with 5 starts sign t plus 1 t plus 1 shift square. Okay, so now the user defined signal is this one. Okay, this is the virtual scope. Click on the button. What we find, our input signal is this and this. So we can change here sampling frequency 430. See the sampling frequency here. So in this manner, again, we can take outputs from here also. We drag the cursor, select the end where we want to take output here. So this all is about quantization of the signal. So the next one we proceed to properties of linear time invariant system. So start from here. It has two parts. The first part say about linear property. The part 2 say about the time invariant property. So again we will start with the processing lab time invariant simulator. Part 1 is selected. Here we'll cut this and part 2 will be selected here, right? So we have to proceed for the linear time invariant system. In the linear system, we know it follows the property of superimposition and the homogeneity. In the simulator here, so we again click on the browse block buttons. We have 5 blocks. The first one is signal generator. The second one is the gain. Third one is the adding block. The fourth one is the DSP system that have to be verified for the property linear either or time invariant. The next one is the virtual scope. The signal generator we select here. So it takes some time. So at first we take the signal generator here. Click on these buttons, press here and press here. Put the sinusoidal signals, amplitude 3, frequency 5 kilohertz, no problem. We just click on OK button. We find the window disappears now. Again, select other one, several signals. Here we opt a square signal and we keep all these parameters like amplitude, frequency, phase angle as it is. Okay. So now we select the gain sample, gain portion and press button here. So gain we apply here 1. Press the OK button, the window disappears. Again we apply the gain here also. Let gain here is 2. Okay, right? Now what we have selected the first signal as sinusoidal signal. X1, let it is X1. The next we have selected a square signal, let it is X2. Now this signal is passing through the gain. Let's say it is alpha, and the second one passing through the gain, let it is beta. So after this we add all 3 signals here. Okay,
after this addition, we pass the signals from the DSP system. Click here, and we are selecting at first yn equal to twice xn here. So now interconnect all these lines here. Again, as the cursor approach the arrow types area, it becomes red. Select, move, and now it is connected. Similarly, the X2 signal, we select here output and proceed, and input here. So it is the gain here. Now again we add all the outputs. This after that we get after the gain, we select here, move, select again. Finally we get the reddish type structure here. Reddish type, the area becomes reddish type. That means we can end our signal here. Now this is connected. Again we proceed like this. Now it is connected. So output of this summation is now fed to the DSP system. We select here and move along the straight line and end here where the circle becomes reddish type, ends here. So what we have done here, we have taken x1, again we have taken x2, so and it is amplified by alpha. So alpha x1, the second one is beta x2. We are adding x1, alpha x1 plus beta x2, and we are getting the signal, another signal here x3. This x3 is passing through the DSP system, and this will be displayed with help of this virtual scope. We place the virtual scope here. Now it has two inputs. The first input we get from this DSP system described above. We connect like this. So now we can see the output at the virtual scope corresponding to the first system. Now we have to verify it is linear or not. So we now take again, select this signal, place here. It is also a sinusoidal signal. We keep all the amplitude frequency as it is and press the OK button. Now the window disappears. This X1 passes through now DSP system. We are selecting the same DSP system that we have selected in the first design, yn equal to twice xn. Now press the OK button, this window disappears. Again we select the signal here, and it is a square type signal. Now press the OK button, the window disappears. Again select the DSP system, the press here and select one of the system like yn equal to twice xn, press OK button, the window disappears. After this we pass it through the gain. Gain first one, because here it is x1, so we provide the gain 1 here. Next we select here and place here. The gain is 2. Okay. So after this we add both the signal. So now we are interconnecting all these blocks like this. Connect as this. We are connecting the DSP block and the gain like this. Again we are connecting this gain to the addition. This. Again we are connecting this DSP block. Now we will connect the DSP block to the gain. Finally we will connect the gain to the addition like this. Finally, now what output we are getting? This is the x1. After passing through the DSP system, it becomes y1. This is x2. After passing through the DSP system, it becomes y2.
Now we are amplifying the signal here. Now it becomes alpha y1, it becomes beta y1. Now we are connecting all these. Finally, what we are getting here is the y3. Now we are connecting these two. So this is the whole system. With help of this, we verify the linear property of the system. Now we go to the virtual scope. What we find? Both y1 and y2, what we have obtained, both are same here. That means, what does it mean? The selected system is linear system. Again, we can change here. Now we will check the whole combination for another system like yn equal to x twice n. Okay. Again, we select here yn equal to x twice n. Okay. Again, we select here yn equal to x twice n. Okay. And go to the virtual scope. What we find here? This system is also linear system. Next, we have more options here. We can go one by one. Yn equal to x square n. Select here. Okay, press OK button. Next, yn equal to x square n. Okay. Again, yn equal to x square n. Okay. Now we select this button. What we find? The y1 is not equal to y2n. That means the system is not linear one. Next, select this one, yn equal to xn plus 2. We verify one by one, each signal will verify. Now again we get ESP system here, yn equal to xn plus 2. Okay. Again we are expressing here yn equal to xn plus 2. Okay. Now we go to the virtual scope. What we find here? Again, this is not the y1 and y2, both are not same. That means the proposed system is not linear system. The last one, yn equal to e to the power xn. Okay. Yn equal to e to the power xn. Yn equal to e to the power xn. So see this, what we find? Difficult to say it is both are same. That means the system is not linear system. So we have studied with this experiment the system is linear or not. The first property we have studied. The part 2 deals with the time invariance. Now move to the part 2. Again, here in the part 2, we will click on the browse block buttons. A window appears. It has 4 blocks: signal generator that we are known with, and one is the delay block, the third one is the DSP system, and the fourth one is the virtual scope. So we have to check the time invariancy of the system. So in the time invariancy, what we understand, if we delay the input by a particular time period, then the output is also gets delayed by that particular time period. So at first we will take the signal, we will delay it and pass through the DSP system, and we'll observe on the virtual scope. And later on, we will again take the signal, pass through the DSP system, and the output is delayed by the same clock pulse. And both are observed on the virtual scope. If the both signals are same, that means the system is time invariant here. So select the signal generator, drag and place here. This is the sinusoidal one. We take the sinusoidal signal here. Amplitude, we keep 3 and 5. Frequency, phase angle for convenience, it is 0 here. We can set as per our convenience, as per our need also. Okay. Window disappears. Now delay block. This is delay. We are delaying by 5. Okay. So DSP system we select here and place here. So we are selecting the first one, yn equal to xn minus 1 plus 2. This is the system that we are selecting here. Okay. Again, we take the signal generator. Same signal we are taking, sinusoidal signal. Okay. Next, we will take the DSP block.
place here DSP block. The same system we are selecting here, yn equal to xn minus 1 plus 2. Okay. The next one, we will take the delay here. Place the delay here. So we are delaying with 5 by 5. Okay. Now we will take the virtual scope, place here. Now it is ready. So we have to interconnect all these blocks. So we are taking the sinusoidal signal here. We are delaying here. After the delay, the delayed version of the input is passed through the DSP system, and it is observed finally on the virtual scope. So interconnect this. Click here. Now signal generator and the delay block both are connected together. Next, we have to connect the delay block and the DSP system. So what we find, the both blocks are now connected. Delay block and the DSP system both are connected now. So next we have to connect the DSP system to the virtual scope. Connect in this manner. So what we are getting here, xt minus 3, it is passing through, it is yt here. Now this signal is xt, it is passing through the DSP system. We are connecting like this. Now signal generator and the DSP system is connected. So the signal xt is passing through the DSP system, and it is the yt now. So yt is delayed by the delay block here in this manner. Yeah. Now the delay block will be connected to the virtual scope. So we have connection here now. So in the virtual scope, now we'll see the results, observe the results for both the systems. What we find. The same system we are observing here. That means, and one more cursor, there is a cursor, here is the cursor. By sliding this, we select the value for yn and y2. What we observe at n equal to 44, y1 is 3.09 and y2 is 3.09. For another, randomly we are selecting n equal to 59. The y1 is 0.91 and y2 is 0.91 again here. That means that both are same. What does it reflects? The selected signal, selected system, yn equal to xn minus 1 minus plus 2 is a time invariant system. Next we select yn equal to twice xn. Okay. Again he will select here yn equal to twice xn here. Press OK. And we will observe on the virtual scope. What we find? Again both are same. That can be also observed with help of this. Randomly we will try to find n equal to 17, y1 equal to 5.7.06, y2 is 5.706. That means y1, y2 both have same value for n equal to 17. Again randomly we are selecting some value, selecting some point, n equal to 71, y1 and y2 at the n equal to 71 both are same. What does it mean? The system is time invariant here. One more system we have yn equal to 0.1 nxn. Select this here. Again we select here yn equal to 0.1 nxn here. Okay. What we see here, is this time invariant? Of course it is not. We are not getting same value for every places. See here, we have different value. So we cannot say it is time invariant system. Next we have xn cos 20n. Okay. Again we select here yn equal to xn cos 20n here. It is selected here. Now we will see on the virtual scope. What we find? Different values. For n equal to 30, it is different. N equal to
n equal to 31, it is different. So we conclude this system yn equal to xn cos xn is the invariant system. So combinedly we want to observe, because in this experiment we have 4 systems: yn equal to xn minus 1 plus 2. We have seen the result for yn equal to twice xn, yn equal to 0.1 n xn. Similarly, we have seen the results for yn equal to xn cos 20n. In the previous one, which one is we have done for linear, to verify the linear property of the system, we have this one. One thing is common here: yn equal to twice xn. We select here twice xn, select here. Yn equal to twice xn, we select here. Yn equal to twice xn, we select here. We see it is not satisfying the time invariant property, but it satisfies the linear property. That means the system is not LTI system, that we can see here. So those systems which are LTI have to satisfy both properties simultaneously at same time, linear and time invariant. So for linearity, we are imposing here superimposition. So we are amplifying, scaling the signal and adding the signal and passing through the DSP block. Similarly, for what we do here, we are DSP system we are using here to produce the Y output. For the x1 we are getting y1 here, for the x2 we are getting y2 here. Again both are amplified here, and adding we are getting y1 here. On virtual scope, what we find here, this one is this system. So this is all about LTI system. Yes.
So I believe that in fact you had gone through 3 labs and you would have understood actually most of the things related to LTI systems, sampling and other stuff. So if you have any questions, we'd be happy to answer it.
Dear participants, if you have any question regarding today's session, then please type them up in the chat box of a Zoom control panel, and I will bring those questions to the presenter.
So there is one question, can we design our DSP system from Preeti actually? So I mean, I believe that you might be asking about whether we can have our own DSP system right from the scratch, containing different modules within that. I believe that in fact if you're targeting some specific application, maybe something like speech processing or something like that, maybe you'll have to use different blocks. But of course, you can come up with a system also using some of these experiments. But these experiments have to be done individually. Connecting them together would be a challenge, of course. But you'll be limited to these experiments only. This is what you need to do. So other than this, there are some questions regarding, can we add more equations such as difference equation? So that probably would not be possible, reason being that we have very specific to the list of experiments which has been given here, right? But difference equations, I think it's not possible. Whatever possibilities are there, you can just explore those inputs and use them only.
I have allowed
So,
all the participants to. Yes, sir. I have allowed all the participants to unmute themselves and are free to ask a question.
Vijay sir, I have one question.
yeah, please.
In the block and whatever circuit diagram you have done, so whether is there any possibility to give the wrong data, or whether it will pop up with some message that you have selected the wrong input. So is there any way, or it will not say anything?
Because the input is already defined, sir.
So actually, your question is quite valid. I think that would be even more valid in case we are coming up with some connections. So the hardware connections would surely say up that the wrong connection has been made. But if you're putting up the data within those specific limits only, so that would only be simulated. Other data would be discarded. Actually.
Okay, it will not accept that thing.
Yeah, it will not accept. It will accept only within that range.
Range is given. Okay, thank you.
So hope so all of you have gained. I am getting a lot of thanks message. So hope so this session was quite beneficial for all the candidates, and they'll take it forward at their institute also in case they are faculty members, and the students would also start exploring them as much as possible. So we'll meet up again tomorrow with experiments related to digital electronics. So hope so that would be quite simple to understand, and we'll try out that we see how many wrong connections we can make, so that we can learn also from those mistakes. Normally it is very appropriate question, because when we come up with actual experiments, we do come across certain problems. It's not that straight away we are going to make right connections. There are a lot of wrong connections also that we make, and that is how we learn also.
Yeah, thank you, sir.
Thank you, presenter, for the very informative session. Yet in the last 1 hour, we have got an excellent feedback in the chat box. Thank you, Mr. Gyanin, for implementing it. Thank you, Vinita ma'am, Head ECE, for joining us. Thank you, all the participants. We will meet tomorrow with other important session on virtual labs of digital electronics at the same time with the same link. Thank you again, all the participants.
Thank you, and bye to all of you.
Dr. Kaushik, thank you.
Thank you.